Hi, I'm back and I'm going to talk a little bit about some of the other features inside of HEMI2. Like any modeling package, you can change the covariates either by changing which ones you load in, or you can say don't use in model by right-clicking on the name of the covariate. You can also, of course, change the coordinates of the response curve and actually modify the response curve. This usually is only done if your data doesn't represent the full range of a species and you have documentation on what its range is. You could also use it theoretically when you have no data from the field, but you have documentation on the range of a species. The real big features inside of HEMI2 to talk about are the Monte Carlo settings. They're available through the dice here for Monte Carlo, a nod to the gambling Mecca in southern France. And if you click on that, you'll see first the number of iterations. It's set by default to 1. The reason for that is because that will go very quickly. Normally, of course, you'd set it much higher, but it's going to take a lot longer. And these are the default settings. It will do a jackknife automatically. You can output each iteration's inputs if you want to see what was input each one, but I don't recommend that because this is going to generate a lot of data. The only thing that's really critical at this point is the temp drive that it's going to put it. By default, Blue Spray uses ST temp, so I'm just going to go to my C drive and make sure I have an ST temp folder, which I do. Oh look, it's got an old HEMI2 run. I'm going to delete that. So now I have an empty folder in case I want to go look at this or save this run later, which is pretty common. Now there's a bunch of different Monte Carlo options that you have, but first I'm just going to run one without actually doing any noise injection or any Monte Carlo. I'm just going to do one run so I can show you what the output looks like. The output comes up in a web window, and here you'll see all of the settings, the input data, and then the overall results. So here's our average habitat map, and then it will also do the standard deviation, the minimum or maximum habitat, and the minimum habitat that was found over all the runs. Now, of course, because we only do one run, the min, the max, and the mean are all going to look the same, and standard deviation is going to be all zeros. Then we have the response curves, the AUC curve, or RC curve, and then the AUC value. Now this also has min, maximum, and the mean and confidence intervals, but because we didn't inject any noise, you can't see those. And then the response curves, which will have the same. And then here's our jackknife results, running the first covariate by itself, the second by itself, the third by itself, first and second, first and third, second and third, and then with all of them. And this will give you not only the mean AIC, but standard deviation, the delta, the AIC weights, the mean AUC, and the standard deviation AUCs. Okay, this is much more interesting when we now go back and we run it not only a few times, like I'm just going to do 3 times, but also let's inject some noise. So normally you wouldn't inject noise into the occurrence at this kind of a spatial extent. You do that for your smaller extent. But let's say we did a small extent study and we have GPSs and our data is in meters, and we know that the data has a standard deviation of about 3 meters. This is actually, I'm in geographic, so this is going to inject 3 degrees. It's going to inject noise with a standard deviation of 3 degrees from a normal distribution. This is going to inject a lot of noise. Okay, but you do the same thing if you had UTM data from a GPS in meters and you had 3 meters of standard deviation. I'm doing this in degrees because then you'll be able to see the features and see the confidence intervals and everything that appear on the web page. So it's now running. The progress bar appears in the upper left. Should drag it back down. And now you can see there were 3 iterations. Didn't do any sensitivity testing. Here is our mean habitat map, which should look very similar to the previous one. And then we now see that we do have an uncertainty map, and we have a standard deviation, okay, for, this is the standard deviation computed between all 3 runs. So taking the habitat maps for each run and computing the standard deviation for each pixel in each of those 3 maps. Then we have the maximum habitat map. So this is the maximum pixel value from all 3 runs. You might use this if you wanted to do something like monitor an invasive species and you wanted to go a little bit on the side of saying, well, where might it live? Especially given the heterogeneity of these environments. We might want to inject some noise and say, okay, this would be a maximum area. We should monitor this entire area. And then you also have a minimum map. This you could use for establishing an endangered or threatened species or reintroducing a species, because this should be very good habitat for that species. And now we can see that with our ROC curve, we're starting to see the mean value for the ROC curve, and then the minimum, the maximum, and a 95% confidence interval. Again, as we inject more noise, these will separate more. I'm going to jump down to the response curves, where you can again see that we're getting the response curves with a mean response, and then a min and a maximum in red, and the blue in the confidence intervals. And you can see that these can get pretty extreme as we inject noise, but also typically non-uniform. So some interesting things happening as we inject, especially spatial noise. Now these histograms show the performance measures. So a histogram of all likelihood values, log likelihood, histogram of the AUC values, and a histogram of the AUC values. And notice none of these are showing a normal distribution, which is what we would hope for as we inject noise. However, it's because we only have 3 models that we're running. So yeah, these we need to run more models up the iteration. So jackknife, similar. We've got our AICs, and we can see that our mean AIC, our best model, is going to be which one? Well, the delta AIC shows us that immediately. Again, that's just running precipitation. How strange. Here's for the jackknife. Again, our AUC, best one with just that, with noise injection. Now remember, these are going to be a little bit lower because we've injected noise. They're not going to be quite as good as our original model. And then we have statistics for each iteration, and we can see that there's not a lot of change between these different ones. These accumulation curves are something Melissa Kimball created, and this shows us where we've stabilized. And you can see that these are not stable yet. The performance measures are bouncing all over the place, so we need to run more iterations. So we can do that simply by upping the number of iterations, but if I ran 100, it's going to take a few hours, so I typically do that overnight. Instead, I'm going to show you that we not only have occurrence noise injection, which I'm not going to turn off, but you can inject noise into the covariates. So in other words, I can say, well, my precipitation values, these are based off of weather measurements, and these are from bioclim, and we actually know that they have a fairly wide uncertainty with them. So I'm going to inject plus minus 10, which I believe is what the bioclim data shows. Of course, this needs to really be researched. Oh, and it should be uniform distribution. So I'm going to go from minus 10 to 10 on the noise injection. Okay, now also notice that there's a raster-based noise injection as well. So on the left is value-based noise injection, or this is going to inject this noise equally across the entire predictor variable raster. If you want to do variable noise injection, in other words, have higher noise injection where there's higher change in elevation or slope, or if you downsampled a DEM and found the standard deviation of the original data, which you can do in R or in Blue Spray, you could then use that raster to do raster-based noise injection. And there you just pick the distribution, and then you pick the mean and standard deviation for normal, or for uniform, the min and the max rasters for that. That's a little more complex, so I'm not going to get into too much here. But I am going to go ahead and run this just so we can see what the results are. And again, I only did 3 iterations, so the histograms and the stability diagrams are not going to be very good. But we can take a look at it to learn about it. And I probably need to fix the progress bars. Okay, so as we scroll down again, our average, there's our standard deviation of our habitat map, our maximum and our minimum, and we can see that injecting noise didn't have a lot of impact on the response curves. We're not injecting as much, and it does tend to have less impact when we inject it into the covariates because we're directly modifying the values. When we change the coordinates, that's going to move the coordinates around where the species was found. And again, I did it with a fairly large spatial distance of standard deviation of 3 degrees, so that's going to be 300 kilometers. So that's going to move it across different predictor values quite a bit. Effectively the same effect, but at a different magnitude. So now we've got our same information with the jackknife results. And we can again see, our delta AIC is shifted. Interesting. So it's now saying that the second and third predictors are the ones that gave us the best AIC. And up at the top we can see that, the first one is coldest month, second one is warmest month, and the third is annual precipitation. Interesting. So these two are now giving us the best model, right? 1 and 2 are giving us the best model. So that is precipitation, which is what we'd expect, plus max temp warmest month. So that also shows that because before I believe it was just annual precipitation gave us the best model, the little bit of noise injection, suddenly the best model shifts, which would mean I'd be suspect about, how good is this model, or this one, over these other ones that also have pretty low relative AIC values. So all of these that have low delta AICs would be potential candidates. I would probably eliminate these ones that are much higher. Do that fairly quickly. Just running temperature by itself doesn't tend to do well, and running them together doesn't do well. So we really need precipitation in there, is what this is saying, with higher confidence than I had before without doing the noise injection. And then again, here's the stability diagrams, which we really need to run like 100 times, and then those would stabilize out and we'd even have more confidence. Just really quickly, you can also do sensitivity testing. This will go in and jiggle the control points on the response curve. So in other words, it will fit the model, okay, and then it will go in and jiggle the coordinates a little bit to see, okay, how accurate do these have to be? Or do we have a pretty robust model? And again, you can pick the distribution, and then for normal, the mean and the standard deviation, and for uniform, the min and the max. For validation, you can do a 70-30 training split just by using 70% for training, or you can change this to whatever amount you like. It only supports cross-validation based on percent test and training. And then you can also bring in a separate validation set. So what we've done in the past is created some random data externally, so you could do that with any cross-validation approach you want. Bring in that validation data set, and it will run the model with the current data that we have in Blue Spray, but then it'll validate it against this other data set, and the columns in that data set should exactly match the one that's currently loaded in Blue Spray, and you'll be good to go. Alright, there is also some help available in Blue Spray, and of course I'm available for questions. Have a good day.